Okay, so let's start our class today. Assalamualaikum warahmatullahi wabarakatuh and good morning to you all. So we will start with our quiz and I'm going to explain how you are expected to answer your quiz. As usual, that's what we always do. And after that, we will, when you finish your quiz, and then of course we are going to do our lectures as usual. Okay, so for that, then I'm going to go to presentation mode. So hopefully everybody you have downloaded your quiz number 4. And now let me explain how you should answer the quiz. I'm going to explain the questions to you. So I'm going to go to presentation mode now. By the way, if you haven't done so, you please make sure that you fill in your attendance. The link is given on the chat section. Hold on, let me find where is the quiz. All right, this one. So do you have what I got here on the screen? We have this trust structure. Can you respond to that, please?
Yes.
Okay, so that is your structure, which is a trust structure, two-dimensional, consists of 3 members. Okay, and you see that we have 3 joins on our structure. Supports are provided by 2 pin joint support on the left there. And the loading is 1000 Newton downward at the joint on the right. Also, you can see our global coordinate. We call it global coordinate. Sometimes they call it reference coordinate. Global or reference coordinate X, Y. So that is your structure. So your job, of course, number 1 is you are going to build finite element model of this structure. And of course, it will consist of 3 nodes and 3 elements. Why 3 nodes, 3 elements? We discussed it last week. And I specify here that the node numbers are going to be 1, 2, and 3 to make it simple. And element numbers also 1, 2, and 3. Of course, the configuration, the setting, everything is up to you. So as long as it is 1, 2, 3 for the nodes and 1, 2, 3 also for the element, then that would be fine. Okay. So number 1 is put numbers on this structure so that you can build your finite element model. Once you finish your finite element model, okay, which can be different from student to student, then get the element number 1, your element number 1 based on your model, your own model, okay, and then state the orientation angle. What is the magnitude of the orientation angle? Okay, and also you do that for the element number 3. And the way you answer, you need to draw that element. You need to draw that element, okay? And then you decide to which direction is your positive local axis, and then you measure your theta to that positive local axis, the way that we discussed last week. Okay, so that is for element number 1 and element number 3. And I want you to draw it. Without you draw, that means you don't understand. And then finally, hold on. Do I have somebody try to get in here? Nope. Okay. And finally, the last question is, Look at node number 3. Look at the node number 3 of your finite element model. It can be anywhere in your model, depends on your model, and then state the value of f3y. Okay, state the value of f, just like what we have done in our previous quizzes. So one thing here that I need to mention, that this structure, okay, the structure is having the same length. So each member is having the same length. All right. So the consequences is that the angle, the internal angle, is going to be 60 degrees. All right. So this is going to be they call it isosceles triangle, meaning that each member is having the same. Each member is having the same length. That means the internal angle, I call it internal or corner angle, is 60 degrees. All right. So that is what you have learned long time ago. That when you have a triangle that looks like a triangle, definitely, and each member here is having the same length, then the angle of the corner here is going to be 60 degrees. You need that information. Why? Because, of course, you need to state the orientation angle. All right. So this is a vertical, of course, this member. Okay, so with that, then of course you are able to answer this quiz definitely. So now my time is 8:17. 8:17. Okay, then you need to submit the answer to that email as usual. Not later than 8:30. All right, not later than 8:30. Okay, so if you have studied, you understand a triangle, then this should be very easy to you. Any submission after 8:30, I'm not going to accept. Okay, so that will be your submission to my email as usual. Okay, you can start now. Okay, so I'm not going to accept any more submission. You have, I think, almost 20 minutes, probably 15 minutes more. Okay, so that was your quiz. I hope everybody enjoy your quiz. Yeah, the quiz is actually very easy. You can finish in 5 minutes if you understand triangle, and also if you understand the basic concept of how you will determine the orientation angle. Okay, so that's what we discussed last week actually. So let me explain your quiz. Okay, not everybody can submit on time. Yeah, but that's quite normal. This is quiz. Quiz means that um, you do based on what you understand and based on the time given. Okay, based on the time given. So if the time is 5 minutes, that means you submit at whatever you can have in 5 minutes. And because this is online, then instead of 5 minutes, I give you 10 minutes. So that's the idea. Fine. So let me explain what we have just now. So for that, then I will go to presentation mode now. I forgot to. Uh, I don't. I don't forget it, but I think now a good time to start recording. So let me try to start recording this session. Okay, good. Now it's being recorded and it is being shared now. Okay, so that is your structure that you need to answer. Number one, you have to build your finite element model, of course. And next, you will decide for element number one and also for the element number t, what is going to be the orientation angle. And this is very important because when you do truss, and next you are going to do frame, your answer, the way you analyze, the way you do the analysis calculation is going to be based on the orientation angle of element. So that's why if your orientation angle is if the way you answer is not based on the proper procedure of analysis based on the orientation angle, then whatever you do is wrong basically, because you make mistake from the top, you make mistakes from the beginning. So the most top is of course your finite element model. If your finite element model is wrong, then whatever you do after that is going to be wrong. So let's say you have done your finite element model and we are working with truss, we are working with a frame, for example, then if your orientation angle is wrong, whatever you do after that is also going to be wrong. I'm going to illustrate that later when we go for a truss example. Okay, so this is your structure. Which by now you must be yeah, you know this structure very well because you've done your quiz. So I'm going to go to this here. Okay, so I hope everybody can see what I have here on the screen. Can you confirm that, please? This is Microsoft Paint. Could you respond to that, please?
Yes.
Can, sir.
Yes.
All right, so what you have there on the screen is the same structure, okay? The same structure on the left. On the left is the same structure. So, right. That's rather big. Let me slide. Okay, no, we can only do 100, 200, 300%, so I cannot do it. Anyway, so that is your structure on the left, and that is the way I do my finite element modeling, the numbering. Your answer might not be the same to what we have there on the screen. In my case, I hope you can see the mouse, the cursor here. That's node number 1. Below here at the bottom here, node number 2 as seen there on the top, and node number 3 is on the right join. Okay, you don't have to be in this way, your finite element model, as long as it's 1, 2, 3, and the sequence, it doesn't matter. It doesn't matter. And the element number is as given here. Okay, so now if I ask you to do finite element model, okay, for your structure, this is what I want. This is what I want. So your finite element model must look like that. You have the element, you have the nodes, you have all the numberings, you have the axis, y in this case, and please also draw the support. Please also draw the support. So this is your finite element model. Anything less than this, then of course I'm going to deduct your mark, definitely. Okay, probably not on this quiz, but on the test. By the way, ODL test 1, exam 1 is going to be in May. If I'm not mistaken, in 2 weeks time or so. I have checked again on the test calendar. Okay, so you have to prepare for your first test, which is going to be in May. I cannot remember what week is that, but it's going to be in May. And for your information, the test is going to be up to the material of the test is going to be until frame. Okay, frame is the chapter after trust. All right, so that is your, back to your quiz. That is your finite element model on the left there. So over here is element number 1, over here element number 2, and down here is element number 3. As I mentioned, this is going to be 60 degree. That's the angle. It is also going to be 60. And over here, you have also 60. All right. So meaning now, based on this information, which I have explained to you before the quiz, then you know the angle. You know the angle. Let's go to element number 1 first. Your question is element 1 and 3, the orientation angle. Okay, so over here I'm going to show you for the 3 elements. So this is element number 1, all right, and you know that is global axis x. Okay, and I decided that, as remember last week we talked about the local axis, and I suggest to you that the local axis is from the low node number to the higher node number. In our case here, that's not compulsory. But that's ideal. All right. So that is going to be x local, which is from node number 1 to node number 2. So I'm going to do it there. All right, so that is X local. And I'm going to write down the symbol of X local like that. All right, so that is X local. It should be caret. It's not very nice, but anyway, you know what I tried to draw over there. And now, as we discussed last week, our orientation angle is measured from X global to X local, which is that one. Okay, then that is our theta. So it is 90 degrees. Okay, so it is 90 degrees. So if somehow element number one in your case is this, then your theta is 90 degree based on our my suggestion last week that X positive local is measured from the lower node number to higher node number from 1 to 2 in this case, then that is your positive X local direction, and theta is measured from X global to X local counterclockwise positive, then that means your theta is going to be 90 degree. 90 degree, all right. Sorry, this is not very nice, the writing, but anyway. Right, so now let's go to element number 2, which is this element. So now, X positive global is to the right, horizontal to the right. Now let's decide the positive X local. My suggestion as before is from low node number to higher node number, from low to high node number. So that means from 2 to 3, which is going to be that angle, sorry, that axis. So that is X local. That's X local, all right? And don't forget, that is our X local from 2 to 3. And X global is, of course, a kind of, yeah, something like that. That's the axis of X global. And theta is measured from X global to X local. Nice. Okay, so do I know the angle? Yes, of course you know the angle, of course, because of here the angle is 30. Okay, so that is 30. So meaning your theta is going to be from there, right? That's your theta. That's your theta. So theta is going to be 330 degrees. 330 degrees. So that is your theta. Nice. So now, I repeat again. For this element number 2, let's say the positive direction is from 2 to 3. So that is X local. Okay. Then that means your theta is going to be measured from positive X global to positive X local. So that's your theta. What is the angle? Of course, you know the angle because you know that this here is a T. Why it is a T? Remember, this is 60. Look, this is not number 2, right? This is a T. So meaning now the rest of the angle to this horizontal is going to be 30 because you need to have 60 and 30 to become 90, right? So, well, that's what we have. It's something that you need to understand. Definitely, you have learned this in your, if I'm not mistaken, your primary school, sekolah rendah. Fine. So now we know our orientation angle for element number 2. What about element number 3? So this is your element number 3. Now, X local is going to be from node 1 to node 3. So that is going to be X local. And I am going to draw the top hat here. I call it top hat sometimes. The English word for that is carrot. Okay. And of course, the X global is, it is going to be to that direction, which is my X global. And as usual, our theta is measured from X global to X local. Okay, so that will be theta. And of course, it is going to be 30. It is going to be 30. So theta is going to be 30. Fine. Why it is 30? Of course, we are talking that angle, right? From X global to X local of this element over here. And we know it is already 60. So it is going to be 30. All right. So with that, then, you know how to answer your quiz. Now, let's say, for the element number 3, this is just, you decide that I'm not going to follow the Cikgu, for example. You like it that your X local, for example, is going to be to that direction. Okay, that's your X local. That's fine. That's fine. Because I don't ask you to write down the equation. If I ask you to write down the equation, then it might be, you might make mistake. But now, in our case here, that is the node 1, that is node 3. So you see here, now I decided to have this X local from 3 to 1, that will affect the equation. But at the moment, we are not writing equation, okay? So it doesn't matter. But now let's say you decide that's my X positive local. What are you going to do? Then, as usual, don't forget to draw your X global, which is that one. And now you need to measure it like that. So that is going to be your theta. And in this case, theta is going to be 180 degree plus 30 degree. Okay, 180 plus 30 degree. So you know your theta. Okay, so now that is your quiz. So I hope you learned something here, because when you do finite element, you need to understand all these angle, the orientation. Okay, you need also to understand your local axis, global axis, which is easy as long as you understand the basis and you study, of course. Last week we talked about it, and then of course you got the recordings which you can learn reading at home. So hopefully you got the full mark here, and yeah. So I hope you learn something from here. So I think by now you realize that the quiz is important. The quiz is important because that measures your understanding. And from the quiz, I know whether you study at home, whether you learn at home, whether you prepare yourself or you do not prepare yourself. And also I understand from the quiz whether actually you understand what you learn. Okay, so from there, then the quiz is a good measure to me of who you are and what you are. So, and then by knowing who you are, what you are, then I can, hopefully I can give a better lecture. So that's the idea. And of course, doing quiz is to force you to study, to force you to study. I cannot imagine if I don't give you quiz, I'm not sure whether you are going to prepare yourself properly or not. By doing quiz, at least, hopefully you prepare yourself, okay? All right, so yeah, that is our quiz. I So now we have done 4 quizzes. So from the 4 quizzes, there are students who couldn't submit on time. From the 4 quizzes, there are students who, because did not attend the class, then couldn't do the quiz. Well, that's normal. That's the way a quiz done. Yeah. So now we got the minimum number of quiz 4, and then hopefully I can give you more quizzes so that you can always be prepared. Later on, those quiz are just average. So if I got total, let's say 5, 6 quiz, for example, just divide the total number with the number of quiz, and then that's going to be your quiz mark, all right? And make sure if you submit your quiz, you submit fully, meaning if it is 2 pages, make sure you submit 2 pages, because otherwise, then of course, your mark is not going to be full mark. So it's going to be pity. All right, so yeah, I hope the quiz is useful to you. Okay, so with that, then I'm going to get a break here, and then we are going to start at 9:10. 10 minutes past 9. We are going to finish today with example on trust. So that's what we are going to do today, example on trust, and then we finish chapter on trust, and we finish our lecture today. All right, so see you at 9:10, 10 minutes past 9. Thank you. All right, now we are going to start again. It's 9:10 now. Okay, so what we will do now is we are going to discuss trust structure, two-dimensional trust structure, and the theory of trust, the element equation of trust. We discussed it last week. So that means um, you are well prepared for us to discuss this example. You know the theory, and last week we did also lab on trust, three-dimensional trust. In our lecture, we will talk only two-dimensional trust. And if I test you on our test one in May, then it is also going to be two-dimensional trust. And you have done your quiz as well. So now you would be, by now you should be very, very okay when we talk about trust. All right. So I'm going to go for presentation mode now. It is also recorded, so you can watch again the movie later on. So I'm going to go to presentation. So this is the example. We have a trust. What you have here is a finite element model. So somehow the model is as what you see over here. I don't understand why this axis line is shifting up. This line should be between this node and that node. But anyway, so two elements, okay, node number one, node number two, and node number three over here. I hope you can see the mouse, the cursor. We have two elements only, one on the left, on the right. Here is element number two, and the dimension is given here. So this is 15 square root of 2, and from here vertically it is also 15 square 2. That means, by the way, be careful, this 15 square root of 2, okay, is not the length of the element. So the length of the element number 2, for example, is, of course, you need to do Pythagoras, yeah, based on this dimension and then dimension, this and these dimensions, then you can find the actual length of your element. The external force is at node number 3, then 1,000 pound, okay, 1,000 pound, and of course, node number 1 and node number 2, as what we observe here, these are supports, where the supports are. So, excuse me. And xy is, of course, the coordinate axis. The material is given here. It is steel. It's given in pound per square inch, 30 power to 10 power to 6. And the cross-sectional area, they are the same for both element number 1 and element number 2. Okay, so you have everything. Then you can solve this problem. Number one, of course, you need to, so this is your finite element model, and then you need to calculate the element equation. And before that, of course, you need to have your element length, right? So for the element 1 and element 2, the length is going to be based on this Pythagoras equation here. Then you know that the length of each member, each element is going to be 30 inch. So make sure that you know how to do this. Otherwise, you are going to make a mistake from the beginning. Okay. Once you have this, then of course you are ready to calculate your element equation. And so the way we calculate our element equation is going to be based on this. You need to know your theta, you need to know your x local axis, and then you will have for every, at each node, you'll have two displacement and two forces. So that means your equation is going to be based on this equation. You have force matrix, you have displacement matrix with the relevant nodes associated with the element, okay? And you need to calculate, just like bar, you need to calculate AE over L, you need to calculate AE over L. And inside here is going to be based on the sinus and sinus of theta, which is the orientation angle. So now we are going to do it. So let's come back to this here. So now let's go to equation number 1. So by the way, AE over L, you need AE over L. Okay, that's AE over L. You need it there because, of course, we will have AE over L inside our equation. So simply just A multiplied by E divided L. This L here is, of course, the length of the element, which is going to be 30. Okay, so for the element number 1, the first thing you need to establish is going to be the theta, the orientation angles. That's element number 1, connecting node 1 and 3. Okay, so I can scroll up. That's element number 1, connecting 1 to 3. And as we discussed last week, I suggest that the equation is going to be based on x local axis, which is positive, from low node to high node. So low is 1, high is 3. Yeah, so that is your x local. And because of that, then your theta is going to be 45 degree. 45 degree. Then the sinus and cosinus you can calculate, okay, as given on the right here. So based on that, then you write down your equation. You write down your equation. So 1E6 here is AE over L, and inside here is based on your sinus square, sinus multiplied by sinus, right? Based on our equation. One thing that you need to observe here is that it is written 1133. 1133. Why? Because the positive x local is from 1 to 3. That means you start with 1 and then follow by 3. So that's the way we do it. That's the consequences. That's the consequences of having this local axis direction positive from where to where. The same for displacement. So that is our element number 1. All right. Next, element number 2. That is element number 2. As I suggest, okay, that x local is from low to high node number. Okay, so that means x local is going to be from 2 to 3. Okay, so that is our x local. from 2 to 3. So I'm going to write X local over here. All right, from 2 to 3. And of course, you know your theta. You know your theta measured from X global to X local. And you can have your equation. Now, please take a look that our equation is from 2 to 3. 2, 2, 3, 3. So that's the nice thing about it. Because if you decide that your X local is to that direction, okay, that is your X local, your theta is not going to be 135. Your theta is going to be full like that. So your theta is going to be different. That's number one. Number two is, of course, it is going to be written from 3 to 2. So it's going to be F3X, F3Y, F2X, F2Y. So that's the consequences of having from 3 to 2. Okay, so that's the reason I suggest that you do it from low to high, low node to high node number. Then you are going to have increasing node 2, 2, 3, 3 rather than 3, 3, 2, 2. So that's the reason. But it is not compulsory. As long as you know your mathematics, you know how to rearrange matrix, then that's fine. Anyway, so now we have element number 1 and element number 2. Now you need to construct your element equation. Sorry, structural equation. So this is your structural equation. Not element equation, but structural equation. And you see here, it is 6 by 6. 6 by 6. Why it is 6 by 6? Because if you look at your structure, you have 3 nodes, 1, 2, 3. This is not bar. This is truss. When you do bar, or when you do spring, every node is 1 degree of freedom. X only direction. When you do truss, every node 2 directions, 2 degrees of freedom, X and Y. So meaning, now you got 3 nodes, you have 6 degrees of freedom, X, Y, X, Y, X, Y. Meaning that you are going to have D1X, D1Y, D2X, D2Y, D3X, D3Y, because you got 3 nodes. So it is going to be 6 by 6, your structural equation. What's the consequences? You need to expand your element equation first. This is element equation number 1, 1133, all right? So you need to expand into 6 by 6. And that is the expansion. So this is element equation number 1, but in 6 by 6. Please take a look. Please observe that anything to do with F2X, 2Y, D2X, D2Y, they are going to be 0 on this matrix. Make sure your mathematics is up to par so that you understand this expansion matrix. Should be okay with you. So initially, it is only with F1 and F3, but now you insert F2. The same, D1 and D3, but now you insert D2. The same for element number 2. Initially, it is 2 and 3, the node, but now you expand into 6 by 6, which you need to insert F1 and D1. That's the reason why this row, they are 0, this column, they are 0. And the rest here is similar to what we have at the top here. Make sure you know how to do it. If you cannot do this expansion, then I can guarantee that you cannot answer your test number 1. Okay? Right. So now once you do expansion, your job next is you combine. You combine element 1, element 2 after expansion. Okay? Then that's what you have, 6 by 6. So you need to really look at this example for you to be able to understand fully the thrust analysis. So now we arrive to structural equation, okay, and it is 6 by 6. So now it is external force. This is external force. F1x, F1y, F2x, F2y, F3x, F3y. So now let's look at our structure, our model. Okay, F1x, F1y, these are the action. Then it is unknown variables. It can be 0, it might not be 0, we do not know. We have to calculate first. F2x, F2y is also reaction. F3x is 0. It is not variable, F3x, it is 0. It is 0 because you don't see any applied force here. It is 0. F3y is 10,000, positive. Now you begin to see why I keep asking you the same question during the quiz. I keep asking you the same question during the quiz because by doing your quiz, then you know your mistake. For example, the quiz last week, still many students doing a lot of mistake when I asked them all these external forces. Be careful, right? Be careful. Now you begin to see the beauty of the quiz because you know what you do not know. Fine, so now you know the external forces. Which external you know, which external you do not know. Where are the variables? What are the fixed point that we know? Okay, now let's look at displacement now. Displacement at node number 1 and at node number 2, they are 0. The one xy, the 2x, d2y, they are 0 because it is spin joint. It is not roller, right? It is spin joint. So meaning it cannot move to the direction of the prescribed axis, x and y. At node number 3, okay, d3x and d3y, these are unknown. They can move, Whether they are 0 or not, we are going to calculate. What we cannot state is that they have to be 0. Of course, no. They can move. So the number can be anything, including 0. So d3x and d3y, these are unknown. You need this information. Why? Because this is your equation, but you need to introduce the boundary condition. And the boundary condition in this case is the displacement at supports. They are 0. d1x, d1y, d2x, d2y. They are 0. So I can do all this potong-potong, right? I can do the section. Hold on, how am I going to do this? I make it red. So anything to do with d1x is going to be deleted. Like that. And also the column. And also for d2x and d2y, d2x, d2y. So the row and column associated with that, I'm going to delete. So that's what we did 2 days ago. Oh, sorry, 2 weeks ago, not 2 days ago. When you learn about how you introduce the boundary condition. So now we end up with only f3x, f3y, and d3x, d3y, which I can write down here. So now f3x, f3y, I know the value, of course. F3x is 0, f3y is 10,000. That means if you don't understand your external forces, then you are going to make a mistake here. And a typical mistake from student is that over here, they only write 1001, 1001. They forgot this. Okay, they forgot this one here. You see, because 1 is 6. Make sure that you do not forget that 1 is 6. Because if you forget, then of course, you are going to make mistake here. So this is the structural equation after you introduce the boundary condition. 2 by 2 now, 2 by 2. You can write this in this way. So they are the same. They are the same. Now, of course, you can solve this equation. 2 equations with 2 unknowns. 2 equations with 2 unknowns. Of course, you can find your d3x and d3y. So this is your answer. d3x is 0. d3y 0.01 inch. Now d3x is 0. Let's look at our structure. d3x is 0. That means this node here is not going to move left, not going to move right. If you see this kind of result, you should be happy. You should feel relief because now this 3x is 0, which is logical. You have symmetrical structure. Left the same as right. Dimension left the same dimension right. The load is purely vertical. So you will expect that this node is only going to move up. The motion is only going to be going up, not horizontal. So d3x will be 0, and you will expect d3y will be positive because it is going up. Let's check the answer. Indeed, positive. So you can feel more comfortable looking at this result now. Next, reaction forces. Okay, before we go to reaction force, do you have any comment, any questions so far? I begin to lose my voice, by the way. Okay, any question? Fine, so let's carry on. So our job now is to find the structural reaction, okay, reaction forces. So it is very simple now. You have d3x and d3y. What you need to do simply, you need only to come back here and look at this equation. So this is our structural equation, which deal with external. Now, you have all displacement known. What you need to do is simply just substitute the magnitude of the displacement, the value, yeah, d1x up to d3y. And then you can calculate your structural reaction forces, which is F1x, F1y, F2x, and F2y, which you can calculate because now you know value of d1x up to d3y. And if you calculate correctly, then you will have the answer like this. F1x is minus 5,000. F1y minus 5,000. F2x 5,000. F2y minus 5,000. So let's look at how we can draw this. F1x, F1y minus 5,000 each. Let's go up. Minus 5,000x. So it will go to the left. Minus 5,000 y. So it is going to go down. Why it is going to go down? Because it is positive y going up. So negative left, negative down. What about reaction at node number 2? F2x positive, F2y negative. F2x positive. Okay, so it is positive to the right. F2y negative going down. All right. So that is what is happening here. Of course, you can write down the value of what you have over here. So now it is going to be 5,000. It is going to be 5,000. Same on the right, positive. And over here. So now you see here, I have all external forces. And of course, don't forget, you have also this. So these are the set of external forces on our structure. Now, sigma x have to be 0, sigma fx must be 0. Sigma fy also must be 0. Over here, sigma fh is 0 because this 5,000 is going to be countered by that 5,000. 0. Sigma y is 0 because this force 10,000 going up is going to be balanced by 5,000 left, 5,000 right, total 10,000 down. So meaning, yes, they are going to be 0. So meaning now, you can expect that what you do is going to be correct. If they are not 0, of course, it's going to be wrong. It's going to be wrong. So anybody who submit your answer to me and the sigma fx, sigma fy external is not 0, then yeah, that means very simple, you don't understand what you are doing, as simple as that. And that is dangerous, because if you make mistake, then your analysis is going to be dangerous. People might have accident because of that. So now we have done this external forces. What about internal forces? Very simple. For every element, you can calculate the internal force. Let's go to element number 1. So that's the equation. Now you have your displacement for element number 1. d1x, d1y, d3x, d3y. And of course, this is your internal forces. F1x, F1y, F3x, F3y. What you need to do now is you need to attach this internal force to our element. Okay, F1x, F1y, minus 5,000, minus 5,000. Okay, so that is your forces. Minus 5,000, meaning to the left, minus 5,000, meaning going down. Now, F3x, F3y, both are positive. So, 5,000 F3x, 5,000 F3y. So now you have your internal force. And you can get your resultant. Your resultant, you can have it, okay, which is going to be that one. So this is your resultant F1. How to calculate the resultant F1 is, of course, going to be square root of 5,000 square plus 5,000 square. So that is going to be your F1. Right. So this is your internal force resultant F1, which is now the direction is as given here, which is tensile. Okay, so it is tensile internal force. The magnitude is given by this equation. Okay, by given that equation. Now, based on this, of course, you can calculate your stress, which is going to be F1 divided by the cross section of element number 1. So that's what you obtain over there. So another things to observe, to note, is that this F1 is axial, meaning the direction of F1, the axis of F1 is going to be at the same axis of element number 1. So that is the reason why actually the basis of thrust element is bar element. Only bar is axial, and then thrust is a bar in two-dimensional space. So now you can see the proof over here. So that is element number 1. What about element number 2? Element number 2 is as given here. So you have this equation of element number 2. You know the displacement. Okay, and then that is your internal forces. So F2x, 5,000, that's F2x, 5,000, that's F2x. F2y minus 5,000, that's why it is going down. F3x minus 5,000, that's why it is to the left. And F3y as given over there. And of course, as before, you can calculate your resultant, okay, at node number 2 and at node number 3. And then, yep, that is tensile force again. And that is the resultant. Then you can, of course, calculate your stress at node number 2. Sorry, at element number 2. Okay, so with that, then we finish our problem here. You have everything. Okay, so now let's relate what we have done just now. Let's go to this. So, excuse me. This is our external force. That's applied force. These are reactions. Okay, that's what we have done before. So this is our finite element model, our structure, action, and reaction. These are all external force. For the element number 1, here, we have done this just now. Internal forces at node 1 and at node 3. For the element number 2, we have done just now internal forces at node number 2 and at node number 3. So now, let's relate what we have done. Look at node number 1. Node number 1 is support. That's the external forces. Please observe that this 5,000 and this 5,000 relates to that. Okay, this is internal forces. These are external forces. Node number 3, sorry, node number 2 over here. Node number 2, reaction. Over here, internal force, but they're the same value. Let's go to node number 3. External 10,000. Node number 3 belong to 1 and also to element number 2. That means they are being shared. Look at this. Node number 3 according to element number 1. Node number 3 according to element number 2. 5,000, 5,000 cancel, becoming 0. 5,000, 5,000 combined, becoming 10,000. That means what? At node number 3, they cancel each other in x direction, 0x, and 1000 y. That's what you have. Okay, so by doing that, I hope I have related the internal to external forces, just like what we have done with our bar structure last week. Okay, so with that, then I finish this example on truss. And with that, then I finish the example on truss structure. And we finish chapter on truss structure. So then we are going to go to frame problem, frame structure, frame element. All right. Is there any question from
the prof?
All right. If you have any question, if you don't have questions, sorry. Okay. Last chance, any question at all?
Hello, prof.
Yes.
I have a question.
Okay.
So every time we identify the reaction force on the question, does we need to make a summation fx and fy? Yes. To make sure that we got equal to 0.
Yes. The answer is yes. The answer
what
is
about
you don't have yes. Carry on, please.
What about if the answer is decimal places? So sometimes we can get like a 0.000, I mean 0.012.
Okay.
Is it okay?
I think remember when we did bar last week, you got the decimal right. But I think logically we can say we understand whether the answer is actually sigma fx equal to 0 or not, sigma fy equal to 0 or not. So yeah, you need to round up definitely. So don't worry too much about the decimal. Okay, don't worry too much about the decimal because that's not the point. The point is that based on your observation, then you understand that it is balanced. What we want to make sure is that the external force, they are balanced, because if the external force not balanced, sigma fx equal to not 0, for example, what does it mean? It means that this structure is going to move. The structure will not move. When we talk static problem, there is not going to be any motion. If sigma f is not 0, that means there is going to be motion, because sigma f not 0, meaning F equal to ma. When you did dynamic long time ago, F not equal to 0, meaning ma is not equal to 0. That means a is not equal to 0. That means you have motion, you have acceleration. All right. So yeah. When we do tests later on, I don't ask you to prove sigma f equal to 0. No. I don't ask you to do it. But mentally, you need to do it, because otherwise your answer is going to be very funny, you know. It's becoming obvious that you don't understand what you are doing if you submit the result, and then I can see clearly that the external force is not balanced. A correct answer, the external force must be balanced. Otherwise, of course, there is going to be motion. So that's what we do not want. What about the decimal? So you look at it, it's not exactly the same, but of course, logically you understand, right? Whether it's going to be balanced or not balanced. So actually, sigma fx, sigma fy, for example, 0 or not 0, that is a good way so that you can detect whether your answer is actually wrong or whether your answer is actually correct. Okay, so I hope that answered the question. Any other question? Okay, so if you have no question, all right. So we are going to meet on Wednesday. On Wednesday, the first part, I'm going to explain to you the basic, the modeling of frame. Okay, frame is going to be more complicated, more calculation. Okay, so we are going to discuss that on Wednesday morning, right? And then the next session on Wednesday, the subsequent session on Wednesday, I'm going to show you on ANSYS how we will do frame analysis, okay? Frame modeling and analysis using ANSYS. And I try to do quiz on Monday next week so that you are always going to be prepared on whatever chapter that you study, okay? All right, so I'm going to return the quiz number 4 to you as usual by the end of the week. I try to do quiz as many as possible to train you. The quiz total is only 10%. Yeah. So if you do not score excellent in your quiz, you still have 90%, you know. So look at the quiz as a as a means to measure yourself. So you understand what you do not know, what you don't understand. Okay, so I think that's it for today. I don't forget your attendance. So I think that's it. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Selamat berpuasa and be safe. Thank you.